Okay, let's see. Yeah, I think now we basically finish all the tests, and your only thing to really submit before the exam will be your lab number 5, right? Please check the deadline. That one actually push forward as far as I can. But make sure you actually did a required study for abstract classes and interfaces. So we're going to finish the discussion about inheritance in general today. I think given how deep we actually talk about the various subjects about inheritance, following abstract classes and interfaces should be no problem. It's more like a small extension to what we talk about. There's no new rule that you should really learn about abstract classes or interfaces. It's mainly about the keywords and also usage scenario you have to apply. All right, take a look at the learning materials I give to you. You should have sufficient time to really get these two topics studied. And they will be covered in the exam. All right, if that can motivate you a little bit more. Programming test number 3 that you had yesterday. I will reach out to the TA tomorrow or over the weekend, and hopefully we can start the grading process from Monday. And I will try to see if we can push to really give you the result and feedback in a week to 10 days time. Hopefully by the last class, all right? I can release the grades and also the marks and the feedback for programming test 3. And for your exam, I made an e-class announcement yesterday. Sorry, not yesterday. I think yesterday. Yeah. So about the exam review session. So indicate your availability if you're interested. Most likely you'll be over Zoom, maybe just to get as many people join as possible. Indicate your availability, and then I will confirm about the time and also link next week. Okay. And about the course evaluation, just to show you guys, I think we're doing pretty well. Okay, that's kind of the score right now. I think, it's completely optional. If you're still interested in participating, feel free. The deadline will be today. All right, just do your part if you're interested. Again, completely optional. I'm not going to see any of the result until January. So whatever you put, it's not going to impact me in any way. All right? Anyway, feel free. All right, guys, any question about the course you want me to clarify? Anything? Yes. Yes, recursion is going to be the final topic, which I'll start today. Yeah, but I think for recursion there, I'll kind of explain why we kind of choose to cover recursion as a final topic. I'll explain that briefly. But I'm going to make it very explicit about what you should really study for the exam. Okay? Yeah. I'll talk more about your exam on Tuesday. I'm going to release maybe some PDF guide about number 1, the format, and number 2, about expectation, and number 3, I'll try to make some example questions for you and some tips about how you should study. All right, so I'll do that on Tuesday, next week. If no further question, let's now move on. So today, we're actually going to finish off the discussion about inheritance. So what's really left will be about method parameters and also return values, and we're going to combine these two with polymorphism. And then I'll speak a little bit more about overriding. There will be some interesting application that we can also look into. And that will be it. So if you find the pace too fast, slow me down. Otherwise, I'll make some small assumption as I go through the code. And then, because many of the things are not new, they're basically what we have discussed so far. So again, if I'm too fast, let me know. Okay. All right, let's now do a quick recap. And then we can now go back to what we need to cover today. So last time, let's see where we are. Yep, so last time we basically talked about this concept of class cast exception. So the principle you got to remember is as follows. Class cast exception is a runtime phenomenon, meaning that the cause of it should really have to do with the variable's dynamic type, number 1. Number 2, the way to judge it would be, let's say your cast over here compiles, meaning that it's casting from the static type downwards into iPhone 13 Pro. It's a downward cast, which compiles. And then, will a class cast exception occur? The way to judge would be, look at the dynamic type and look at the cast type. Can the dynamic type fulfill the expectation of the cast type? If yes, there's no class cast exception. If, for example, the Galaxy S21 Plus, in this case, is not a descending class of the cast type, in which case it cannot fulfill its expectation. In that way, you're going to run into class cast exception. All right, that's something you have to remember. All right. And of course, if you forget about the rule during the exam, Everything will go down to expectation. Hopefully, you can make it so logical in your mind so you can always derive what we have been talking about as a result. All right, any question about having class cast exception? Apparently, you have to know how to determine yourself whether it's really going to happen, depending on what the dynamic type is and the class type is. Okay, we did a few more examples, and you can look at the slides, and the exercise will be up to you. And this diagram here basically just categorizes the whole inheritance hierarchy into different categories. So given the static type and dynamic type for a particular reference variable, so we basically mark them down first. And then category number 1. For those classes for which you can do either an upward or downward casting, namely ancestor or descendant classes. So all these classes are so-called the upward or downward casting. And for all of them, they will be compilable. Right? Meaning that if you try to cast your variable of static type, let's say Android, to any one of these, it will be compilable. So that's the first category. And easily to see, anything that's not compilable will be non-compilable. That means those classes are neither ancestor nor descendants. All right? And we further look at those classes that's going to make the cast compile. We can divide them into 2 categories. The idea will be you want to look at the dynamic type and think about runtime. At the runtime, any classes for which your dynamic type can fulfill its expectation is going to be class cast exception free. Meaning that Samsung dynamic type can fulfill itself and also all its ancestors. So these classes are so-called class cast exception free. On the other hand, let's say these classes over here, for example, let's say, can I cast Samsung into Huawei? It will compile because it's a downward casting. On the other hand, it's going to run into class cast exception because Samsung over here is neither, well, it's basically not the descendant class of Huawei. It's not going to fulfill its expectation. All right? That's something we spoke about last time. Right? So when you review for the exam, take this page over here as a summary about the different scenarios for typecast. All right? Good. And then we did this little nice example here, right, about typecast, right? You can review it for the details. The idea will be just for compilation, you can cast from any class into another class by doing more than one cast, one followed by another. I can definitely do an upward cast and then downward cast. But you might still run into class cast exception. In this case, C, the dynamic type, cannot fulfill the cast type over here. That's why you're going to get into class cast exception. Right? So this one is also consistent with what we talked about in the diagram over here. Okay? And we talk about the instance of operator. And it's going to be some objects denote, it's going to be some expression pointing to some objects of certain dynamic type. And the instance of is going to return true if the object's dynamic type can fulfill the expectation of what's on the right-hand side of the instance of, typically a class name. So in this case, we're saying the dynamic type over here can fulfill the expectation of Y, which should be somewhere up in the hierarchy, like ancestor class. Right? By definition, a class should be able to fulfill its ancestor's expectation, but not the other way around. All right? That's about the instance of. And then we did several examples here, and I owe you guys some summary about the abstract page, which I'll do today, right? I'll do that in just a moment. And then I'll do that first, and then after that, we'll do a quick recap about the method parameter, and then we'll do more example. All right, I'll come back here in just a moment. Let me do this page over here, which I didn't do last time. So this one here really try to summarize again about instance of operator. So I want you to look at these 3 lines over here. Line number 1 here, we are trying to do some variable assignments, like a substitution. In order for this line here, for this variable assignment to compile, we know that this must fulfill the expectation of this. Or you can say B is a descendant class of A, right? In which case it is, because B, you can see, is a lower one than A. All right, so number 1 here should be straightforward, but you can also look at the textual description here. Let's look at 2 and 3 here, right? That's the main focus. Whenever I want to do a typecast, let's say I want to cast obj, declare to be here. I want to cast obj into some type. I'll leave the type here open, question mark, question mark. And it would be safe. Whenever I try to do the typecast into something, I can check to see whether obj over here is really an instance of that thing I want to cast into, right? That's the pattern. Now we want to ask ourselves the following question. Under what circumstances will this expression over here return true? All right, that's the question. I'm here leaving here question mark, question mark. So what will be the range of clauses I can put over here so that obj instance of this is going to be true? All right, that's the question. All right, I'll write it down here, and then we'll answer that together. Okay, so the question here, I'll put it here. That's the question. What can the question mark, right? You can see the question mark is over here. Be to make the instance of operation return true. Evaluate to true, how about that? This is a very critical question for you to bear in mind. What can be the question mark be to make the instance of? Yeah, I really meant to say instance of over here. Okay. All right, that's the question. And you want to go back to the very definition for instance of. We know that it's only going to return true if the dynamic type of obj, in this case, is B. Only if B can fulfill the expectation of question mark, question mark. Now, given that B is already here, what clauses can be fulfilled by B? Definitely want to go up, right? Basically, by definition, all the ancestor clauses of B can be fulfilled by B, right? That's the definition. So I'm going to do a final annotation here. Basically, go from B to its parents, grandparents, all the way to the top of the hierarchy over here. Right? You can see this part here, right? It's not strange to you, should not be. B ancestor all the way to the top. We call it ancestor path. So these are all the ancestors for B. And we know that these are the clauses whose expectation can be fulfilled by dynamic type B over here. So they're going to make instance of return true. All right? That will be the conclusion, basically, for the summary. Oops, sorry. There's one here. Ancestors of dynamic type B. Right? You can see dynamic type B here. i.e., B can fulfill their expectation. What about other classes? If you try to put on this question mark here, if you put one class over here, or maybe one class over here, it's going to return false. In which case, you should not try to cast. You're going to write into class cast exception. All right? I think that the main value for this page over here is really, number one, for you to, again, try to see variable substitution, instance of check, and also typecast, right? You see all the three things. And try to look at what do we expect to see? What do we expect to check on each one of them? And then you want to know very well visually, when you are given a particular dynamic type at that particular moment, all the classes being ancestor of the dynamic type can be cast into without any class cast exception. That's why in the instance of, it's going to return true. All right? That's the main message. All right? All right, any question about this? All right, if you're still not exactly following, study, and then come back to me, maybe later, if you find the need. All right, that's good. And let's now go back to one more part of the recap, and then we'll continue from there. So what we did last time as a last part was to talk about method parameter. And it's very easy to make a connection between method parameter to inheritance, call by value. Because whenever we got call by value, that simply means we got some implicit assignments. Let's say this. I have a method call here, calling this method here. And I got a caller context, I got this callee, right? The way to connect the caller and callee is by call by value, which we learned earlier. Call by value tells us there is an implicit variable assignment, which will try to assign the arguments into the parameter, right? Just remember the order. That's really important. So once we understand that there is some implicit variable assignment here, it goes back to our comfort zone. In order for this variable assignment to be valid, what should be the rule? The static type for the argument O should be a descendant class of the static type of the parameter Rs, right? What does this tell us? This tells us this O over here can be of any descendant classes of the resident students in this case. All right, that's where we were. Guys, any question until now? We haven't done any example yet, but we're going to do that. But before that, any part you want me to clarify about this connection to call by value? That's really the critical step, right? In order for you to really judge to see whether a method call is going to be valid, you should definitely think about call by value. So you can link from the arguments to the parameter, right? That's the main thing. All right, so we're going to do some example about this method call. Hopefully that can build some intuition in your mind. And then we're going to see by having this kind of method call, we are able to create the so-called polymorphic collection. That will be the next one. All right, one step at a time. Let's now do some example here. Okay. All right, so let's now review very quickly about the classes. We have our student management system class, okay, and then we have our students array, SS. And remember, every element in the array has a static type, students. And we got three methods here, add RS, resident students, add non-resident students, and also add students. The difference is, if you look at the three parameters over here, they have different static type. One is resident students, the other one, non-resident students, and the last one, students. Right? You can see the difference here. And we're going to play with them a little bit, just to try to call each one of them with different arguments and see which one should compile. We are only talking about compilation. We'll see what the consequence is at the runtime in the next example. So we got 1, 2, 3, 4, 5. We got 5 variables. You can see they got the first 3 variables got static type students. This variable here got static type resident students. And this one here has static type non-resident student, right? That's good. And we're going to use somehow each one of them as arguments or input to the method call. Right? For example, we got all these here. I want you guys to at least pause a moment to look at these method call just for 1 minute. I'm going to number them. You really want to kind of see yourself whether you can judge which ones are going to compile and which ones are not going to compile. Okay, we got 10 of them. And one thing to note, you can see the first block are calling add RS. And the second block there are calling add students. So let's talk about the first block first. All right, 1 up to 10. Think about each individually, whether it should compile or not. I think that once we got the first one understood, the rest will be very easy, right? So always the first one is important. All right, just pause for 1 moment. All right, now, anybody would like to try? How about just number 1? Compile or not? No, you guys are good. Okay, can anybody try to explain to me? Go ahead, please. You're 99% right, but I will say the following, okay? I would say the static type for the arguments, which is students, is not a descendant class of the static type for parameter resident student. That's how I would say it, okay? Pretty good. All right, for the first one, let's now write it down completely, okay? So you can see that this one here at RS, which correspond to this method here, and we can make the connection here, which will be the implicit assignments RS is assigned to S. All right. So this one here, you can see S has the static type will be S1. I beg your pardon. S1. All right. S1 has the static type students. And for the parameter RS, it has a static type resident students. So it boils down into the following question. Is S a descending class of RS? Yes. So that's why it will compile. Sorry, it will not compile. I beg your pardon. What I'm talking about. It's like everything right except for the conclusion, right? Let me do it again. Because student here is not a descending class of resident student, so it will not compile. Okay? Not compile. Not a descending class. All right? That's good. So this one will not compile. And what about this one here? Will not compile, right? Because there's, again, these are just students. Doesn't matter what the dynamic type is. Doesn't matter. All right? No, no. And this one here will compile. Thank you. So RS, you can see that this one here was declared to be resident student, which matches, even better, matches that. It's a descendant class of itself. All right? Very good. All right. This one, no. All right? Very good. And for number 6 to number 10, this one, I can tell you all will compile, all of them. All right? And the reason you really want to see from higher level is this. We are calling as student here. And the as student here has a very, very high or generous parameter type. You can see student here simply sits at the top of the hierarchy. It's almost like a push smartphone, right? And then polymorphism tells me the following. When I actually have the parameter here as, when I do call by value equals some argument over here, polymorphism tells me now what can be the acceptable type over here. Any of the descendant classes of students in this case. That's going to include all classes over here. So there will be something that we're going to see in the next example. In order for us to build like a polymorphic collection, you want to have your add method, like a mutator here, the parameter type as high as possible in the hierarchy, because that's going to allow so many different possible dynamic types. That's something we'll see. Right, so all these are just going to compile. For example, you can see RS over here was declared to be resident students. That one is a descendant class of student. Right, that's something you can see as well. Yeah, you will also see the correct answer from the slide, but all of them are going to compile. All right, any question about this example here? Good. Now, I would like to go over something called, oh, just before polymorphic collection, let's go over one more example. Beg your pardon. Here, one more. And let me show you where this corresponds to on the slides. If you look at the slides, it will be, okay, that's the thing we just did. All right. Okay, and it will be from slide number 79, all right, all the way to, I'm going to talk about all of them at one go, just easier for you to see the picture. It'll be from 79 all the way to, bear with me, to 82. All right, 79 to 82, these slides. And let's now take a look. The way you can study this page goes like this. We have some reference, we got code number 1, code fragment number 2, and number 3, okay? They look very similar, except the following setup difference. All the variables here have the static type students. Static type is the same. Students, students, and students, the same. However, the dynamic types are different. One will be just students. One will be non-resident student. The other one is resident student, but all are valid because of polymorphism. Each of the dynamic types is simply a descending class of the static type. So they are all valid. And then I'm trying to create another object here, SMS, for student management system. And then I'm calling the add resident students method. If you recall, it was declared like this, where the resident students parameter has this static type. Okay? And now I'm passing this, and passing this. And you guys answered pretty well from the previous page. All these are not going to compile because the static type over here for the arguments, when I pass them into here, they are not a descendant classes for the resident students because they're simply students, right? Now, and the story continues like this. In order to make this particular method called compile, I can do some anonymous cast, meaning that I want to do some typecasting without giving it a name. This is an anonymous cast I'm talking about here. Now, first of all, is this cast compilable? In order to see if that's compilable, you have to look at what's the type of S, students, in all three cases. If I cast that into resident students, of course it's compilable because it's downward cast. All right. Let's now make sure that one is written down for you. So this one here is a downward cast, which is okay. And whenever you realize you're doing some downward casting, you should really alarm yourself right away. Sure, it compiles, but am I going to run into class cast exception at the runtime? Right? In order to determine that, as we recapped earlier, you have to look at the dynamic type here, here, and here. If the dynamic type, for example here, can fulfill resident students, then you will not run into class cast exception. If you cannot fulfill, you'll run into class cast exception. Okay? Do you think writing this line over here into here is going to give you a class cast exception? It will, because the dynamic type over here is students. Student is not a descendant class of resident students. Okay, you write into a class cast exception. So class exception, yes, for the first one. And for the second one here, you can see dynamic type is non-resident students. When I try to do this typecast for that, can non-resident students fulfill resident students? Also no, it's not a descending class, all right? Also, yes, I'm gonna run into class cast exception. And the final one is the only one that's gonna work because the dynamic type is actually resident students. Resident students, dynamic type, can fulfill the cast type, resident students. So we're good, all right? So that's the only one you're not gonna run into, no class cast exception. All right, so it's just a nice way to really show to you whenever you're trying to make a method call, if the argument itself, for example, the argument itself, let's say here, has the static type that's actually not a descending class of the parameter type. You might be able to get around by doing some anonymous casting like what I'm doing here. However, you gotta be very careful when you do it because you might run into class cast exception. So what will be the safest way to do it? You can wrap it around instance of, right? That's something I didn't put here, but you can definitely sketch that yourself. All right, any questions so far about this example here? All right, one more thing about here. Let's say we got another setup. NRS, static type, non-resident students. We got dynamic type over here, just the same, okay? And then when you try to say sms.add_rs, this one here is not going to compile because NRS has the non-resident student static type, the arguments, which is not a descendant class of resident students. So it does not compile, all right? That's why you see a cross over here. So when I asked you about if there's any class cast exception, oh, sorry, let me say one more thing. This one here does not compile, but what if we try to add an anonymous cast over here, like what we did earlier, all right? So this one here, is it compilable cast? All right, that's something you want to think about right away. Think about this way. We will only care to talk about class cast exception if the cast itself compiles. If it does not even compile, why should we care about runtime? Right? That's the logic here. For this cast over here specifically, okay, this one here, I'm going to write it down. For this one here specifically, right, you can see NRS has the static type non-resident students. Can I cast from non-resident students into resident students in a single cast? I cannot. Neither ancestor nor descendant is neither. So it does not even compile. No, because it's neither upward nor downward casting. Right, that's important. All right. So talking about whether there's going to be any class cast exception here is nonsensical for this example here because it does not even compile. You cannot even run it. All right. All right, any question? I think this will be the last example we're going to do about typecasting. So I think we really talk about so many things, about the typecasting, about using instance of, different scenario. That will be something you want to focus on reviewing for the exam. All right. But I think we covered just enough details for you to review. Okay. After this, let's now talk about a very important topic, polymorphic collection. Oh, before that, yes, of course. Yes. Okay. Let's talk about this one here, for example. Let's talk about this one first. Add RS is definitely referring to this method here. All right. And then NRS was declared to be non-resident students. But this non-resident student, is it a descendant class of this? No. That's why you will not compile. Whenever we talk about compilation, we only worry about static type. Mm-hmm. Correct. That's correct. For example, let's say over here, let's say this one, if you only, let's say without a cast, the static type here is students, which is not a descendant class of resident students. But after the cast, as you said very accurately, we are creating an alias. And the alias has a static type, resident students. In that way, resident students is a descendant class of itself. So we are good. Yes, that's exactly the point. Yeah. Alrighty. Okay, so let's now talk about polymorphic collection. And I would like to give you some very quick hints about how you should really study this one here as well for you when you review. So this will be slide number 83. Okay. So this one here, basically, we're asking ourselves a big question. Can we have a single collection or single array storing both resident students and non-resident students at the same time? That's a big question, which we could not in the case where we don't have any inheritance. So what you should do is, of course, we're going to go over the code together. One moment. You will see that at the end of the slides, there is one link over here, right? If you click on that, it's going to link you back to slide 11, which we were maybe 4 lectures ago, all right? So this page over here is also trying to define student management system. But that one there, we don't have any inheritance, all right? In that way, we have no choice, but we have to create separate arrays for every for every class, like a students, that we're going to create for non-resident students and resident students, like a separate arrays. And consequently, we also need to have multiple add methods. We also need to have multiple loops to handle the arrays. All right, so that's without the inheritance. That's something you can also compare and contrast. But if you click on the link again, now we're back here. So that will be the ultimate solution we want to devise. All right, so now my goal is to show you guys how we can build this polymorphic collection of students. That's a very important thing to really notice. That's going to happen at the runtime. All right, let's do that. All right, let's now go step by step. Let's look at the student management system class first. All right, that's the class we're looking at. We have a single array. You can see the static type for every element in the array is students. Right? We can make a note right away here. You can think about the students over here is the static type. Static type of basically the student, I'll say SS for short. SS0, SS1, all the way to the last element. All right, that's important. That's something we also said on Tuesday. Okay, static type. And here we got add students. And this one here, you can see we got the most generous static type for parameter, which is students. All right. So this one here, you want to also alarm yourself right away. The fact that we have some parameter type over here that involve inheritance. This tells us any arguments that's of a descendant class of students can be added. That will compile, right? Any arguments of static type that is descendants of students can be passed as argument. Okay, this is also a very important point. Okay, descendants. And this is indeed what we said about polymorphism, right? You can also refer to what polymorphism is, how it is defined. Okay. And then here we just do the simple assignment, right? You can see the students at some position, at some index is assigned to S. And we spoke about why this variable as assignment should compile last time. All right. That one I can leave you to review. All right. I'll put a circle here, so just remember to review that. All right. And here we got a method called register all, and we want to register a course for all the students, including resident and non-resident. So we simply use a single loop, go over every elements, and then we say students I.register. All right, this is important, right? Again, whenever you see a method call, you want to think about which version of the method is it going to be called, right? So here you see students I over here. Number one, we know that its static type is students. That one we know pretty well because it was declared to be this way, right? And then what about dynamic type? The dynamic type, which I will visualize to you in a moment, dynamic type for the context object here for the register method call can be any of the descending classes of students. RS or NRS. So these are the descendants of the static type. Again, that's polymorphism. Okay? But the register method itself is not as interesting. Let me just remind you very quickly. If you look at the hierarchy here for the students, if you recall, there's only one version of the register that's not really overridden. But when we look at that a little bit later, the get tuition here has one version for resident students. It has another version for non-resident students. That's something we'll pay more attention to, right? But here, you just got to remember, when you actually execute this at a runtime, it doesn't matter whether the dynamic type is here or here. You're just going to execute the same version here because there's no other version available. All right, one thing to note. Okay, all good. Let's now look at a code fragment over here and see how we can build up some polymorphic collection. That's very fundamental to know. To save time, I have drawn a diagram here already, but I'm going to show to you very briefly how it is built. Okay. For line number 1 to line number 5, right? That's basically the code we can start with first. Okay, 1 to 5. So here we got RS, we got NRS, also we got SMS. RS, NRS, SMS. RS is pointing to some resident students objects. NRS is pointing to some non-resident students object, right? Apparently you can see this is a dynamic type. This is another dynamic type. They are stored in the same array. That's something already tells you what polymorphic collection is about. In the same collection, you store objects of different dynamic types. But these dynamic types are somehow share some common ancestor. In this case, students, right? That's the insight. So what you should really know to yourself would be, think about this guy over here is dynamic type number 1. This one here would be dynamic type number 1. And this one here would be dynamic type number 2. Dynamic type number 2. At the same time, you want to also remind yourself, for each of the indices over here, because we're referring to the declaration of the array, each element has a static type students. So here you want to say each SS at index I has the static type students. So what we really have over here is as follows. Each element in the array has a static type students. That cannot be changed. That's how we declare that to be over here. On the other hand, dynamically, we may put in any objects whose dynamic type is a descending class of students, which we do. We have resident students, we got non-resident students. Right? That's a very important fact for you to see in a polymorphic collection. How do we build it? Easy. All you got to do is you're going to trace these two lines of code. Number 1 and number 2. Line number 6 and 7 are the most crucial lines to really watch out for. Okay, let's take a look. Very easy to see. So here we're basically saying we're going to add the students, and you guys can do as exercise to check why this will compile and this will also compile. That's something we just did earlier, right? So I may not repeat that part. And this one here, when we say add rs, rs is pointing to this particular object, right? So if you try to step into the add students, I'll show you very quickly. If you step into the add students, we're going to assign to the some position of students array. In this case, it will be at index 0. Index 0 is going to be assigned to whatever that particular object is, the arguments. And the argument in this case will be rs. So we are saying at index 0, it should really point to wherever rs is pointing to. That's what it does. All right? So after executing line number 6, index 0 of the array is pointing to resident students objects. Following the same logic, if you execute line number 7, it's going to add to index 1 nrs, which is pointing to some non-resident student object. Right? So you really want to make sure you understand how this line is, how this arrow has been executed, and also how this one here has been executed. Basically this one and this one. Okay, when you review. Let's now see a little bit more. I have some check for you right away over here. The way to check dynamic types will be instance of. All right. So we want to do instance of checks over here and also over here. The right-hand side, I enumerate all the possibility. I have non-resident students, resident student, and students, right? Here as well. But on the left-hand side, you can see I try different objects here. The left-hand side here, I'll make it bigger. The left-hand side here, we got array at index 0, which is referring to this object here, right? You can see that over there at index 0 over here is really referring to this particular object of dynamic type resident students. Now we can do the check right away. When I say this instance of non-resident student, true or false? What am I checking? I'm basically checking whether or not the dynamic type here is a descending class of this. Is resident students a descending class of that? No, false. All right. That one will be false. What about this one? This one here, instance of resident students. True. Good, good, good. All right. And then what about this one, instance of students? True, because resident students can also fulfill students. All right. So what I have done was I took one element from the array and tried to check its dynamic type using instance of. And then I'm going to get different results over here, which we'll go over, because now I will have different objects with different dynamic type. Let's see right away, okay? What about this one here, the left-hand side? I'm talking about index 1. Index 1 over here is referring to the object stored at index 1, which is referring to this object here, dynamic type non-resident students, right? So now if I say that expression, instance of non-resident student, true, thank you. What about that one there, instance of resident students? False, it's not a descendant. This one here, true, thank you. All right, so that one there should be, I want to write the right thing, so that one should be true, and that one should be false, and that one there should be true. You can see false versus true, right? Right away. So what we really learned from this page, let me recap, and then we can move on. Right? Of course, you gotta really dive into detail and really appreciate how we can build such structure here. Number one, if you look at the actual class, the collection itself, like an array in this case, the static type is as generous as possible, almost like at the top of the hierarchy, students. By polymorphism, we know that at a runtime, each element may store any objects of descending class of students. Right? That's what we start with. How can we make it happen? You need to have some mutator like as students whose static type over here is also very generous. That can allow any arguments whose static type is a descendant of that. I can add maybe some resident students. I can also add some non-resident students as well using this method here. And then at the runtime, whenever you see any method call over here, you want to think about which version of the method is being called. Right? The way to judge it will be by looking at the dynamic type of that. All right, so we trace these two lines over here, and then we try to compare the instance of when either the first object here or the second object here is on the left-hand side for the instance of, right? They will give you a different result. Okay, one more thing before I can take some question if you have any. And we also try to call the get tuition over here. All right, get tuition. The get tuition over here, of course, it will be more interesting to trace because we got two versions of the get tuition. We got version 1 in the resident students. We got version 2 in the non-resident students. And notice that we are running a loop over here. And the loop is going to go over the number of students in the array. We got 2. We got 1 here and we got 2 here. So there will be 2 iterations, right, for the loop. Iteration number 1. You want to think about for iteration here, right? So the I here, the index could be either 0 or 1. It could be either 0 or 1. 0 for the first iteration and 1 for the second iteration. For the first iteration, you're basically saying students array at index 0. We basically go back to this particular check, right? We're talking about this particular objects. When you go to the second iteration, you're going to have index 1, and we're going to this version here. In that case, we are referring to this object instead with a different dynamic type. Okay, and then one more thing. In the first iteration, we talk about index 0, so we're really referring to this object here. When we call get tuition, which version are we going to call? The one corresponding to the dynamic type, resident students, right? Dynamic binding. When we get to the second iteration and the index or the loop counter is 1, we are really referring to this object here with dynamic type non-resident students. That way, when we call this .get tuition, it's going to give us the version in non-resident students using discount rate. All right? So that's really the insights you want to convince yourself, right? Question? If you're following maybe 50% or maybe more, that's a good sign, but not so much, catch up, right? That'll be something that will take some time. Yeah, question? Oh, then you. Go ahead. Sure. Good, very good. So what you said, I can see where the confusion is. You're right about every element, element index 1, index 0, index 1, every one of them, static type students, I agree, no problem, okay? However, when we talk about which version of method to call, it's a runtime decision. Whenever you talk about runtime, you have to refer to dynamic type. To really refer to dynamic type, you have to draw the diagram by tracing. So now when we talk about this element 0 here, static type is still students, but dynamic type is actually resident students. So that's why when you call this one here in the first iteration, you're going to refer to the resident student version. Okay, and then for the second iteration, you're going to switch to index 1. Static type is still students, but dynamic type here is going to determine the version to be called, which would be the discount rate version in the non-resident students. Okay, make sense to you? Good. Question? Mm-hmm. Mm-hmm. I see what you mean. Yeah, you're quite right. If you simply use the instance of operator to really count, of course, you will see both of these are going to return true, right? So, of course, the way to do it would be you may want to be a little bit more fine-grained about your instance of check. But I would say for our particular example, the student object here usually is not really should not be really created because that one is kind of incomplete in the sense they don't really have either premium rate or discount rate. So we should only create either resident students or non-resident students over here. But let's say if you really want to count, let's say student instances, resident, student, non-resident, you can use the get class. That one can be very precise comparison, but that'll be another story. Yeah. All right, good. Any other questions? Okay, I promise one more for detail tracing. One more. Okay, that one. This is another one, and this one here is going to also try to apply polymorphism, but we are applying that in a different context. We talk about method parameter. Let's now talk about method return value. Accessor, basically. All right, let's take a look. Take a look. All right, so that's something we just spoke about. And okay, this one here. That's something we want to talk about, right? We're going to introduce one more method. Okay, that'll be slide number 86. Okay, very simple method here. We still have our student management system class, and we got our student array, which is good. Also, we got our mutator over here, the same as before. This is the new method that we want to discuss now. And this is what I will call polymorphic return value, because I'm now focusing more on the return type. So the return type for this method here is a reference type, and the class here involves some inheritance. So that's why polymorphism will get into place. All right. Well, as soon as you see this particular student over here, right, you will see that. Okay, I'll put it here. The student here is the static type of the return value. What about dynamic type? It could be any descendant class of students, basically. All right. As soon as I talk about inheritance and also some static type, you also think about polymorphism should apply. So dynamic type should be any of the descendant classes. This tells you that by polymorphism, we know that dynamic type of the return value, I'll just say RV for return value, can be any of the descendant classes. The descendants of students. Right, that's something we can note right away. And to really see how this works, I simply create some local variable. The static type here just matches the return type. Just easier for you to see. Okay, just match. And we say that if the I value here, which is going to be taken here, is invalid for the array, I'm just going to throw some illegal argument exception, right? Some exception there. And what should the method do? Simple. When I call getStudent here, I want to return the student objects, which can be either resident students or non-resident students at index I. That's what I want to do. Okay. And then else part, if the I is valid, I'm just going to do this assignment here. All right. Very quickly, if you look at S over here, it has the static type students. And then we know that SSI also has the static type students. But what about at a runtime? At a runtime, we know that SS is a polymorphic array. Which we just discussed in the previous page. That tells me the following. S may be assigned and objects whose dynamic type is a descendants of students. For example, let's say this. If I just go back very quickly. If somehow S is assigned to index 0, dynamic type will be resident students. S may be assigned to non-resident students. In that case, it will be dynamically non-resident students. Okay? So you can think about these two examples, this one here and this one here, they're kind of related. We build the array first and try to get some value from it using the accessor. All right, so that's about this method here. And let's now trace a little bit about this piece of code over here. They will, this part over here, only this part, is something will be routine. I'll just point to you very quickly. So this part here, we basically have set up the polymorphic array. We got student management system, we got index 0, index 1. They point to different dynamic objects over here, right? That's basically what we did. You can see all the method call here, for example, as students here, that's something we did earlier, right? So this part we don't need to repeat. What I want to show to you is this line. Okay, this line here. And I'm going to do one block with you, and another block will be exercise for you, which will be traced in a very similar way. So this part here, starting from here, all the way to end, the blue one will be left exercise for you to trace. Oh, sorry, let me do a little bit better. This one here is going to be exercise for you. Okay, let's now take a look at this part here, all right? All right, so what we try to do is we try to call sms.getStudents at 0. When you try to step into this method call, it's going to call this method over here with 0. 0 is a valid index, so we don't really go here. We'll go to the else part. That will really boil down into basically s is assigned to ss0. Agree? So that one tells you S is actually going to point to the index 0 object here. All right. And that one there, if you try S instance of either students or resident student, it should be true because resident student is the dynamic type. On the other hand, when you go to this block over here, now I change the argument from 0 to 1. What's going to be returned will be this object instead with a different dynamic type. The instance of it is going to be different, right? That's something I'll leave to you. All right, one final remark. When you try to call s.getTuition here, because s right now is really pointing to resident students, I know that dynamically it's going to call the version in resident students. On the other hand, if I get to here s.getTuition, because now s will be reassigned to index 1, which will be non-resident students. So getTuition should be non-resident student version instead, right? So really compare this line here and this line here and get yourself convinced why it's going to call different versions. Okay. Okay, quick recap. The new thing I would say in this example here is we are focusing more on the return type over here. Once you get the return type itself involved in some inheritance hierarchy, you know that polymorphism should still work, meaning that the return value from this accessor here dynamically can be any of the descendants of students, which can be resident students or non-resident students. And then we try to see how we can do it. And then when you try to trace the code like this, you can see the return value over here dynamically, if you compare this one here and this one here. This one dynamically will be RS, this one will be NRS, right? And everything else will work accordingly. Okay. All right, any question? Please slow me down if you need some clarification, right? But I hope at least you can see what I'm trying to do here. All right, if no further question, okay, let me do a few more things and we'll take a break, okay? We're still good. Okay, this one here will be a table that you will see on the slide. Okay, I'll show you. We're pretty much moving towards the end of the inheritance. So this is something we just went through, and then this is something also we did. Oh, this one is a good summary, which you like something you want to take away. When should you use static type, and when should you use dynamic type? I think I mentioned that briefly before, but let's now repeat again. You only use static type whenever you talk about compilation. Simple, nothing else. Dynamic type would be something, given that your code compiles, what's going to be the runtime behavior? Then you have to get dynamic type into the context for your tracing. And the typical example would be like which version of the method should be called? Dynamic type. Should we get tuition from resident students or maybe from resident students? Another one would be if you want to judge to see whether or not the class cast exception should occur. You also look at dynamic type. Okay? All right, there's a page to summarize about the two different notions. And the table over here, I'll show you how you can read it. Okay. Maybe beyond this course, if you ever have the need in your work to build a compiler for some programming language, if you ever, right? I'm not too sure. But whenever you want to build a compiler which is going to process some programming language that you may define yourself, then this will be the kind of rules you have to implement yourself. Because whenever you want to process your programming language, you have to do something so-called semantic analysis. You want to see if your program semantically makes sense. For example, if I'm trying to call a method that simply doesn't exist in the class, I should not even allow that from the user, right? Something like that. So these are just an example. It's not really like an exhaustive list, but it will give you some idea. The table itself is pretty self-explanatory, but I'm going to go over just one of them together with you so you get some idea. Let's say this one here. Okay? This one here basically involves, number one, variable assignments. Number two, method call. Number three, call by value, right? Three things. So each one of them is subject to a rule. All right, let's now go one by one. Number one, if you're trying to make this particular method call, you have to make sure method m is declared in the type of x. For example, let's say you're calling get tuition. You got to make sure get tuition is really declared in the static type of the context object. It should be a student, for example, right? That's rule number one. And rule number two is really about parameter passing, argument passing. If I'm passing y as the arguments, I have to make sure its static type is a descendant class of the parameter of that particular method m, right? Of course, I didn't include the definition here, but you know what I mean. Finally, what about this particular variable assignment? In order for this one to be compilable, you have to make sure the right-hand side has the static type that can fulfill the expectation of the left-hand side. All right? So if you look at the left-hand side here, this one here, what will be the static type? Well, since we are making a method call over here, we're calling the method m. Presumably, it's an accessor. So you want to look at the return type of m. That's going to tell you what it's going to return. For example, if you look at the get students that we talk about, if I'm calling get students, what should be the static type? It should be students, the return type. All right. So for that one, you're going to make sure the static type for the return value should be a descendants class of the static type here. That's for variable substitution. Right? We got three different rules for you to consider. And your task for the review will be to look at each one of them and make sure you're convinced. All the rules have been covered somewhere in the course. All right? Some of them were covered even earlier than the inheritance lecture. All right, that's how you read the table. All right, you can review that when you prepare for the exam. Any question about the table? All right, this will be the final example about inheritance, and then we'll take a short break. This one here is really about a little bit addition about more detail about overriding. If you guys recall, the object class should be the top of the hierarchy. That's something we learned, just repeating some information here. And then in the object class, we also got another method called toString, which I'll mention briefly after the equals method. Let's now go back to the equals method a bit. Okay, and we want to see exactly, let's say you got multiple versions of the equals method. Which version should be called, right? Let's now take a look. It's interesting to see some tricky case. Okay, this will be the setup. Let's say we got three classes here. We got A, we got B extends A, we got C extends B. Simple one. And implicitly, that's why I got dash arrow here. Implicitly, A extends from objects. I could have also drawn B extends object, C extends object, but it's going to complicate the drawing. We don't need to, right? So this is good enough. All right, so let's say we got C1 and C2, and we want to call C1 dot equals C2. Now, which version of the equals method is going to be called? It depends on the dynamic type of C1. Agree? Dynamic binding. So you should really look at what's the dynamic type for C1. It's exactly C over here. So I'm going to annotate it exactly here. That's the dynamic type. In this case, we're pretty lucky because there is only a single version of the equals method, because we're assuming that none of the classes over here actually override it. This is how things are going to happen at the runtime. We call C1 that equals C2, and the dynamic type is C1. Is there any equals method explicitly overridden here? No. Go to its parents. Is there any overridden version? No. Go to its parents. No. Go all the way to the objects. That's the version to call. The very first one you encounter in the ancestor path is going to be called. That's the principle. Okay, let's see another scenario. So for this one here, it's going to call the object version. That one's pretty straightforward, like a point V1. How about that? And this one here, let's say we're assuming that in class C, we override the method, equals method, let's say. So now we got two versions. We got version here, we got version here. And we got the dynamic type C. And then if I still call C1 that equals C2, which version? C. Because we check to see is there any overridden version? Yes, right here. That's the version. That's also a simple case for you to see. That one is a bit like a point V2. All right. Tricky case will be like this. Let's say we still want to do C1 dot equals C2. And then we know that C1, the context object, has the dynamic type C. But now we have the following. We got object version. We got an overridden version, not exactly in C, but in its parents. Now, which version are we going to call? This one or this one? Okay, in B, intuitively, even if you look at the diagram, you should know that, right? Here's the principle. You go with the overridden version in your closest ancestor. That's something in the term you will see on the slides. If you got multiple overridden versions for you to choose for the dynamic type, here, this is dynamic type. You choose the version closest to you from the ancestor path. All right, so that's the principle. All right, and that one there should really give you the version from B. All right, that's good. That'll be about equals method overriding. Question? Good. Okay, so after this, a little bit about toString method. Only 2 slides, very quickly. And these are the different cases I just spoke about. You can also review them when you prepare for the exam. And the 1, 2, 3, right? We all spoke about them. And for the toString method, I just want to remind you, I'm pretty sure you have done that already in your test and your lab. If you just try, let's say for point, and then you say print out P1, by default, it's going to print out the address for the object, right? That's when the toString method has not been overridden. On the other hand, if you try, let's say here, in the point class, I try to override the toString method to something. That way, if I try to execute the same block of code, let's say here, I still want to try to print out P1. Implicitly, Java is going to call P1.toString. That one there's going to call the overridden version. And that one there is going to give to you, rather than the address, some meaningful thing that's actually defined in the overridden version. Right? That one's also straightforward. All right, any question? That would be the end. Right? You can also try the to override the equals method and toString method for the student classes. All right, so I would suggest if you want to do more practice on the programming, you can definitely try the inheritance hierarchy for students and for the smartphone, right? I intentionally didn't give you any source code for that. I really want you to try if you're curious to find out more about the example and try out all the example we discussed in the class. And then you want to pay more attention to compilation and also runtime behavior, like which version of the method is being called, and also class cast exception. All right, that'll be it. All right, any question about inheritance? That's all I want to say. But I think it's quite a interesting topic there. There are many small topics around it as well. So I really consider this lecture here the most fundamental one for this course. All right, really want you to take away some important concept about inheritance. Any question? If no, how about this? I got about maybe 9 minutes. Should I continue maybe for another 7 and then no break? Okay. But before that, can I tell you that I'm not going to take attendance today. If that's the case, if you want to leave, it's okay to leave now. If you're just waiting for me to, take attendance, right? In case, right? But if you're willing to stay, let's talk about recursion. How about that? Appreciate that. Okay. Okay. I promise. Only 7 minutes. Whatever I can cover. So for recursion, it's going to be the final topic for the course. The reason that I chose not to really cover this first, but rather in the last, will be number one, itself doesn't really fall into OOP. Object orientation has nothing to do with the recursion. Somehow it's in the CRO, so I need to cover that. But number two, I think covering that as a last topic would be nice because in 2101, the data structure course that you take in the winter, this will be a nice transition to there. You're going to need recursion very badly for the data structure course. So I think the later we cover this, the fresher memory will be, right, for you. But anyway. And I want to, I'll see how much I can cover. I'm not going to run over time. We're going to learn about how to solve problems recursively. We're going to learn about recursions on strings and arrays, especially for arrays. I'm going to give you guys very explicit learning resources which you can try, and then I am only going to cover in the exam what I will put in the learning resources, which means if you try those problems, you should be okay for the actual exam, for the recursion part. Okay? I'll talk more about it in just a moment. All right, and also more advanced example if time permits, or we can talk some maybe in the review session. All right, number one, so for those of you who want to kind of get started with preparing for the exam earlier, of course, I will only dive into recursive methods only from Tuesday, but I'll put the slides today. You can definitely go do a little bit self-study if you wish, but these two sites will be the best resources for you to get prepared for the exam. So I think I briefly mentioned coding bad, maybe when I walk over the syllabus, okay? So they got very nice collection of problems about recursion, especially on the array or on different data type. Especially for recursion 1. That'll be more at the beginner level, but recursion 2 will be slightly more advanced. If you can also plan your time to really try as many problems as you can in these two sites, that'll be the best preparation for the exam, okay? And more long-term. To me, the best way to learn about recursion may not be through Java. For those of you who really want to sharpen your skills about recursion, let's say by the time you have to graduate, learning a language called functional programming language will be your best bet. So for those of you who want to spare, see you later. Yeah. So for those of you who actually want to have some spare time over the break to really sharpen more recursion, you can look into this functional programming language called Haskell. It's a very popular one and common one in the industry as well. Okay, that's only for optional. Okay. Okay. So I'll only spend about 2 or 3 minutes just to talk very briefly about recursion, and then we'll continue on Tuesday. So what about the principle for recursion? So recursion is really for the problem that can be expressed recursively. Usually the beginner will find recursion very weird, which I'll show to you. I know exactly where you might be struggling, but I think once you click on you'll be not so bad. It's quite a natural way of thinking. Always remember, when you try to plan your recursive solution, there are 2 things you want to always keep in mind, just conceptual level. You want to have something called base cases, and also you want to have something called recursive cases, right? I'm going to talk about them maybe one by one, okay? Let me just spend 2 minutes or 3 minutes, and then that'll be it. I just want to walk you through this diagram very quickly, okay? Think about whenever you want to solve a problem of recursion, 2 cases. Okay. Basically, we got case number 1 and case number 2. All right. So we got case number 1, which is called a base case. We got case number 2, which is called a recursive cases. Recursive cases. 2 cases. Conceptually, base cases are those where you got some problem which itself is very small. You can devise the solution right away. Like edge cases. Usually you should have at least one for the recursive problem. Okay? And then what about when you got something that's bigger? Say there will be several phases. Let me go over with you. Okay? And we're going to follow this principle as well when we program each problem for the recursive solution. You're basically given a problem that's much bigger. You can see this problem here is much bigger than this one. I don't really have a solution for that right away. It's called divide and conquer. I'm going to divide this particular big problem here into individual problems here. And one thing that's very important, each problem here must be strictly smaller. It cannot be equal size. It must be strictly smaller. For example, this one here is strictly smaller than this. This one here is also strictly smaller than this. All right? Each problem here must be strictly smaller. And here is the phase that will puzzle you the most in the beginning. Somehow, once you have identified strictly smaller problems here, you can somehow assume. You don't need to solve it yourself. You assume there is already a solution for this subproblem. There is already a solution for this subproblem, and etc. You can assume it. Once you have that assumption there, you can somehow try to combine all the smaller solutions over here. Once you combine them together, you're going to get the ultimate solution for the original bigger problem. Okay, so this phase over here, as we'll see in many examples, might be the most difficult one to really understand because it seems very magical when you first see it, but it's not. Once you do the tracing, nothing is magical because everything is going to be executed on a computer. All right, so I would say that's all I want to say about solving problems recursively. You can try to kind of appreciate this diagram a little bit more over the weekend, and then we'll dive into details about recursion from next Tuesday. I'll also talk about the exam next Tuesday. All right, thank you so much. I'll see you next week.